Great, thanks. So yeah, today I'm discussing work that describes an approach for using task and motion planning to train goal condition policies for robot manipulation. Let's set the stage. In recent years, we've seen an impressive expansion of both robotics and AI into automating industrial settings. These are still limited to scenarios like we see here though, environments where you have very low variability in the configurations the robot might encounter. The tasks themselves are mostly small variants off the same basic motion, and the tasks only need a few steps in order to be accomplished. We'd want to extend these into more dynamic scenarios. So for example, here we see an Amazon fulfillment center. This gives us something that's still controlled, but is going to encounter much more diverse sets of scenarios. And so we need to account for more diverse sets of tasks. We also will want to be able to reason over extended sequences of actions in order to accomplish these tasks. You could consider placing an object down low versus having to climb the stairs to place it up high. How might we go about approaching this? Let's look at some of the existing approaches we could try. And as you may have guessed, the first one I'll talk about is task and motion planning. So here I'm going to use a simplified problem to highlight the concepts, and later I'll build back to more meaningful domains. This is our initial state. We're going to have a cylindrical robot with a gripper and some objects, and the goal is going to be grab the green object and move it to a target while avoiding collisions. Now, there are a lot of ways to go about task and motion planning. Here are the citations for the approaches we adopt, and you can refer to our paper for further details. But roughly speaking, we're going to break it into two parts. The task planner is going to operate on a logical representation of the world and produce a sequence of discrete actions to accomplish the goal. Grab the object, place it on a target. Now, these aren't simple subroutines we can just call. We need to turn them into an actual trajectory. So the motion planner is going to start the grasp action, and it's going to go through and produce a sequence of controls to reach the first waypoint. And then I'll do the same thing for the place action. And finally, we have a set of controls that can accomplish the goal. This is where we're going to enforce things such as collision avoidance and kinematics constraints. This isn't a one-way street. Let's add an extra obstacle into the mix and assume the task planner produces the same plan as before. Now, let's also assume the motion planner goes through and tries to refine the grasp. But let's say we're running something like local trajectory optimization and get stuck in a bad optima. The planner is going to say, hey, I can't get around this collision. And it's going to pass that information back to the task planner, which is going to update its logical state to account for the collision and then replan to avoid the obstacle and keep going. And now the motion planner can find a valid trajectory. So to recap, we have two nodes, task and motion planning, and they pass information back and forth until we find a valid trajectory that reaches our goal. So the nice thing about this is because the motion planner only has to operate over short horizons, it can solve problems that have high precision, complex geometric constraints. And then the hierarchy allows us to tractably extend this to problems that may require even dozens of actions. So let's see this in action on a toy problem. Here it gives us a nice smooth motion to grab the object, place it on a target. Now this is all great, but there are some big issues. The first is that task and motion planning is very slow. Actually computing the plan takes a long time, even though we can do it. And in order to transfer the plan from your simulation into the real world, you need to have precise state tracking. So what are some of the other things we could try? Well, this is a conference on robot learning. What if we train a policy? So we've all seen impressive applications of deep learning in recent years to perform complex manipulation from high dimensional observations such as camera images. And because forward inference in a neural net is very quick, this gives us something that's very fast to execute in practice. So to see what this might look like on our toy problem, here we ran proximal policy optimization to train a policy on the same task. Now notice that it's settled into this kind of nudging and bumping along motion instead of grabbing the object and placing it. This is after we ran extensive reward shaping to try and encourage it to first grab the object and then place. What we found was we could get it to either grab it or place it, but not both. This was after training for 10 hours across 60 workers and evaluating several different algorithms, as well as performing hyperparameter tuning. Now, I want to be very clear here. We're not saying that this is the best you could do on this problem, but it highlights that what was a rather trivial problem for the planner to solve is actually quite difficult to train a policy for. And the issue here is that because we no longer have the constraints on the motion, we just have a less precise form of control. We're going to build up small errors over time, and we're going to be limited in the horizons we can operate over. So to recap, task and motion planning is nice because it gives us a precise motion and we can execute it over long horizons, but it's slow and we need to precisely track the world state. Training a policy gives us something that's fast to execute, and we can operate from more general observations such as images. The motion is less precise, and we can't operate over the same horizons. This is where we come in. We propose a way to combine these two and get the best of both. What we're describing is imitating task and motion planning. And now that isn't as simple as that. The first thing we might hope to do is run our planner a bunch, collect some data, and use that as supervision for a policy. First issue is this is just going to take a long time. We've already said planning is slow. If we want to get enough data for supervision, we're going to be waiting a while. But we've already broken our planning into two nodes. So we can distribute it further and run parallel asynchronous copies of each planner so that we can be working on dozens of problems at once. This amplifies our throughput to the point where we can run imitation learning online. We can then use the partially trained policy to further improve planning. We do this by at each step of the plan, first rolling out the policy, and then initializing our trajectory optimizer around that rollout. As the policy improves, the optimizer needs fewer and fewer iterations to converge. This reduces the overall planning time. This has an added benefit as well of helping us to combat trajectory drift in the system. For that, I'm going to refer to our paper. So where does this get us? So here's where we were with PPO before. Now we're training a single neural net to imitate task and motion planning. And notice that we've already seen a qualitative improvement. It is learning how to use the gripper to grab the object, place it on the target. And this reflects a roughly twofold increase in the success rate using only 5% of the training compute that we gave to PPO. Okay, this is nice, but there's still a long way to go. We're nowhere near what we were seeing with the task and motion planner before. So the issue right now is that transitions at high-level actions create sharp discontinuities in the control space. So here we see the trajectory as we move from the end of a grasp action into the start of a place. At the end of the grasp, you need a lot of small adjustments to orient your gripper and grab the object without knocking it away. Once you're holding the object, you can then take large steps towards your goal. This means the policy has to learn to map almost holding the object to these small steps versus holding the object to these large ones. These are very similar observations, and it creates this sharp discontinuity that's very difficult for a single neural net to capture. This isn't the only place this happens. We also see what happens if we change the goal. The controls for the grasp action are the same because the object hasn't moved, but the place action has to diverge to this new location. So how might we go about handling this? Well, we build in action-specific subnetworks, things that will account for each type of action we can see without worrying about the transitions. And concretely, what this looks like is we have a hierarchical policy. We have a high-level policy that takes the goal and the observation, and it produces the action to take as well as the associated parameters. We pass these down to a set of low-level policies, one for each action we could encounter. Because these policies only have to worry about one type of action, they don't have to worry about the transitions, they don't have to worry about the discontinuities. We can then use our choice of action to gate the output of these policies and choose our next control. And we run this end-to-end at every time step. So now, instead of training one policy, we bifurcate our data and train two. And this gets us the rest of the way there on this toy problem. So now we have a success rate of over 99%, and with the same compute we had before. Okay, so we're ready to move on to harder problems. The first thing we're going to do is we're going to have 3 objects now. And the goal is going to be to train from RGB images to place them onto randomly assigned targets. Here we can reach a success rate of 83% after training for 2 hours across 30 workers. If we give the policy access to object positions as well as a LiDAR style sensor, it can place 5 objects 88% of the time with the same amount of compute. Let's move to a more meaningful domain now. Here we see the RoboSuite pick place benchmark. The goal here is to move the 4 objects on the left to corresponding bins on the right. The controls are going to be the 7 robot joint angles as well as the gripper, and the observations are going to be the object positions and orientations as well as joint angles. Our learn policy can place all 4 objects 88% of the time onto their targets after training for 4 hours with 30 workers. This is a bit of an idealized scenario though, because it's a simulation, we don't have a lot of the noise we might encounter in the real world. So we ran some experiments to test how robust the policy actually was. The first thing we did was we corrupted the observations with Gaussian noise. This dropped our success rate down to 64%. We then turned to RoboSuite's built-in dynamics randomization wrapper. So this is going to affect things such as joint stiffness and dampening, the contact solver, as well as corrupting object body offsets. So this is both where you perceive things to be in their orientation, as well as relative orientations of robot links. This dropped our success rate down to 34%. So this is a noticeable drop-off, but we would like to highlight that in our review of the literature, we only found prior attempts that focused on solving one object variant of this problem. We're still solving the 4-object variant here and able to do it 34% of the time. Furthermore, because we're training from object positions and orientations, we would expect those body offsets to have an outsized effect on the performance. So if we remove them and only randomize other physical quantities such as contact solver, joint stiffness, inertia, and so forth, our success rises back to 73%. We're now ready to move to our hardest domain. So this is the Robodesk benchmark. Here we again have a robot with 7 degrees of freedom and a gripper, and the observations are now RGB images and the joint angles. Our goals are going to be 9 very different tasks we're going to want to accomplish. We're going to want to train a single policy that's able to accomplish all of them. We're also going to give it 7 more generalizable motion primitives. So I want to highlight these motion primitives are not specific to the tasks here. They're general things like move to, grasp, and place. So single policy, general primitives. The 9 tasks here are going to be open slide, lift blocks, stack blocks, so forth. Training from the default camera that you see here and the joint angles, we can reach a success rate of 68% after training for 10 hours across 30 workers. Now, one of the issues here is that the robot easily occludes the objects, so we added a camera onto the end effector. With this in place, we were able to reach a success rate of 79% with the same compute, and we can break that success down across the individual tasks here. Now, I want to highlight again, this is a single policy. We're not training an individual policy for each task. So to summarize, we propose a system for efficiently imitating task and motion planning, use that to train a hierarchical goal condition policy, and then evaluate in a 2D-pick place a high-dimensional manipulation problem with 4 objects and a multitask problem from RGB images that we can successfully deploy our policies. Thank you, and yeah, see us at the poster session afterwards.
Thank you, Michael. Maybe one quick question.
Hey, so in the beginning, you made a very good case that there in the pick and place task, there's 2 separate phases, right? But then in the later work, you show that you run these at every time step. So I was wondering, if you run these at every time step, isn't there a chance for this to oscillate rapidly between different sub-policies? So have you ever considered trying to predict how long a given sub-policy should run and then just like let it run for a handful of time steps and checking if it's reached this phase transition?
So that's something we actually were worried about. And one of the cool things is we found we didn't need to do that. So there's a lot of similar work out there that has waited for the policy to converge before transitioning. But what we found was we could actually run it end to end and not have any issues. We were a bit surprised by that, actually. It was a kind of cool result.
Cool, thanks.
Okay, I think in the interest of time, we have to move on. So thank you again.